Keeper 7.1, the substitution rule, or what we like to call U substitution. All right, so this method of integration is basically the method we use to undo chain rule. So if you remember chain rule from derivatives, we're going to undo that or go backwards by using U substitution. All right, so your steps for U substitution. Step 1, you want to choose your U. And generally that's your inside function. So again, if you remember from chain rule, we had like inside and outside functions. Generally your U is your inside function. So it's like whatever's being squared, whatever's being cubed, whatever's in the exponent. It could be whatever's in the denominator. Those are some tricks to finding U. So once you find your U, you're going to determine your basically your du. And du is going to be in terms of dx. So by determining du, you're also determining dx. Then you're going to substitute those values back into your integral. And then it should be some integral that you're able to solve using like our basic rules from last unit. And then once you solve your integral, you want to take out the u and put your x back in. All right, so let's try a couple. All right, so for our first example, we have the integral of the square root of 2x plus 1 dx. Generally, with these problems, you want to figure out what's on the inside or what's your inside function, and that's what you're going to let u be equal to. So in this case, u, we're going to let be equal to 2x plus 1. After you find u, then you're going to take the derivative of u and call that du. So the derivative of 2x plus 1 is 2. So I get du equals 2 dx. All right. Now, I don't have like an extra 2 in the problem. I just have like the 2x plus 1, which I already called u. So this 2 that I have with the du, I'm going to move to the other side. I don't want it really with my dx. So I'm going to say du over 2 equals dx. And from here, I'm going to do a basic substitution. So I'm going to substitute the 2x plus 1 in for u, and then I'm going to substitute the du over 2 for dx. And so I get the integral of root u du over 2. Now I can pull that 1/2 out, or the over 2 part, I can pull that out, and I get 1/2 u to the 1/2 du. From there I integrate, so we know that u to the 1/2 is simply add 1 and divide by the nu, so I get 1/2 u to the 3/2 over 3/2 plus c. Now I want to clean that up, so I'm going to keep change flip it, and when I do that, I'm going to end up with 1/3 u to the 3/2 plus c. And then again, I don't really want that u in my problem because I didn't start with the u. I started with x, so I need to go back and plug the x back in for u. So I get 1/3 2x plus 1 to the 3/2 plus c. All right, so next example, we have the integral of 3x minus 4 e to the 3/2 x squared minus 4x dx. Now, I have it color coded, and I'll show you why in a second. But just note that those colors do mean something. All right, so here's our example. Very first step again is to find my u. And so looking at this problem again, I kind of want to look for the inside function. And looking at this, the easiest way to pick it out is going to be your exponent. So for this problem, we're going to let our u be this 3/2 x squared minus 4x. All right, so this red section again is my u. Now, when I take the derivative to find my du, I take the derivative of 3/2 x squared minus 4x, and I get du is 3x minus 4 dx. Now, if you notice in the problem, this du that we found is this blue piece and this dx part over here. So this whole blue piece is now going to become my du. All right, so when I substitute that back in, I'm left with just e to the u du. Well, we know what the integral of e to the u is. The integral of e to the u is e to the u. So I have e to the u plus c. And then again, I don't want the u in my problem, so I'm going to take that and replace it back for my u. And I get e to the 3/2 x squared minus 4x plus c. And again, you can take the derivative of that to check your answer. The derivative of this should equal the original integral. All right, so our next problem is the integral of 8x over e to the x squared dx. The first thing I'll probably do is to rewrite this integral by bringing that e to the negative x up. So I have the integral of 8x e to the negative 8x squared dx. And so when I work this problem, just like in the last one, I'm going to go ahead and let my u be this negative x squared. And so if u is negative x squared, I know that du is going to be negative 2x dx. Now, again, you really want to kind of look at your original problem and look at what you have. I see the x in my problem. This x from du is right here in the problem. And the dx is also in my problem. I don't necessarily need this negative 2, so I'm going to divide it out. So I have du over negative 2 equals x dx. Now, substituting that back into my integral, I'm going to have this 8 that was in the original integral over the negative 2 for my du, integral e to the u du. Now, we know what the integral of e to the u is. That's just e to the u. And I also know that 8 divided by negative 2 is simply negative 4. So I'm left with negative 4 e to the u plus c. And again, I don't want that u in my problem, so I'm going to replace that back with negative x squared to have negative 4 e to the negative x squared plus c. Now, if you remember from derivatives, we don't too much like to have negative exponents. So I'm going to drop that back down to say negative 4 over e to the x squared plus c. All right, for this example, we have the integral of secant x over pi, tan x over pi dx. Again, I'm kind of looking for my inside function to figure out what my u is. And I know that my inside function is just this x over pi. And so I have u equals x over pi, which means that du is 1 over pi dx. But again, I don't have an additional 1 over pi to use in my problem. So I'm going to multiply both sides by pi to get dx by itself. So I have pi du equals dx. And now I'm going to substitute that back in. When I substitute it back in, I'm going to end up with secant u, tan u, pi du. And then I'm going to take that pi out of my integral, since it's just a number. So pi integral secant u tan u du. And I know that the integral of secant u tan u is just secant u. So I'm going to have pi secant u plus c. And again, I don't like that u in my problem since I wasn't dealing with u to begin with. So I'm going to replace that back in with the x over pi. So I have pi secant x over pi plus c. Next example, we have the integral of 5x plus 3 to the 4th dx. Again, my inside function is this 5x plus 3. So I'm going to let u be my inside function of 5x plus 3. Then when I take the derivative of u, I get du equals 5 dx. But I don't need that 5. I don't have extra 5 in my problem, so I don't need the 5. So I can divide both sides by 5 to have du over 5 equals dx. All right, now substituting that back in, I have 1/5 from the du over 5, integral u to the 4th du. Now using my power rule where I add 1 and divide by the new exponent, I end up with 1/5 u to the 5th over 5 plus c. Cleaning that up and substituting u back in, I have 5x plus 3 to the 5th over 25 plus c. Here we have the integral of cosecant squared 11x dx. Again, asking yourself, what is your inside function? We see our inside function is 11x. So u is going to be 11x. That means du is going to be 11 dx. Or if I divide out by the 11, since I don't need it, I have du over 11 equals dx. Substituting that back into the integral, I have 1 over 11 integral cosecant squared u du. The integral of cosecant I know is, or cosecant squared, is negative cotangent, so I have negative 1 over 11 cotangent u, but we know u is 11x. So negative 1 over 11 cotan 11x plus c. All right, another similar problem, and at this point you guys should start seeing the patterns. Again, my u is going to be this inside, so u is going to be 5 plus 17x. That means du is going to be 17 dx, or du over 17 will be dx. So really I have 1/17 the integral of sine u. Well, the integral of sine is negative cosine, so I have negative 1 over 17 cosine of u, but instead of u I'm going to put in the 5 plus 17x plus c. All right, so here's a little bit of a harder example, but we've done one like this already, so you should be okay. Again, I'm going to find my inside function, which it looks like is x squared. And so I'm going to let u be x squared, and then du is going to be 2x dx, but I don't need the extra 2. So I'm going to divide by 2. Now notice that I have x dx in my problem, and so I'm just simply left with, when I substitute back in, 1/2 integral cosine u du. Now the integral of cosine is sine, so I have 1/2 sine of u, but again u was x squared, so I have 1/2 sine of x squared plus c. Alright, so our next example is a little bit harder. We have the integral of 3x squared over 5 minus 4x cubed. Again, I know I keep saying try to find your inside function to identify your u. This one is not as apparent, but the key for this one is to let your u be whatever your denominator is. So if you have a fraction, a lot of times your u is your denominator. So I have u equals 5 minus 4x cubed. And so du is going to be negative 12 x squared dx. Now I notice in this problem that I need a 3x squared, and I see du is negative 12x squared. So instead of like just dividing by negative 12, I'm simply going to divide by negative 4 so that I'm left with the 3x squared dx that I need. So now du over negative 4 is this whole piece up here, this 3x squared dx. And so when I substitute this back in, I'm going to get negative 1/4, 1 over u du. And we know that the integral of 1 over u is simply ln of u, or ln absolute value of u. So I'm left with negative 1/4 ln absolute value of 5 minus 4x cubed plus c. Alright, so we have something that's called change of variables for our definite integrals. So if you remember, definite integrals are the ones that actually have the bounds. And so we already know how to solve definite integrals. We know that you just take the integral and then plug in the top and then subtract that from the bottom. But basically what this is saying is you don't have to like put it back in terms of x. You can leave the function in terms of u and plug in bounds, but you have to change your bounds to also be in terms of u. So instead of plugging in our original like a bound and b bound, I would figure out the bounds in terms of u by plugging in a and b into u to find my new bounds. And so then I can leave my function in terms of u and solve it out like that instead of changing it back to x. Alright, so here's your steps for integrating with change of variable. Basically, you're going to define your u like we've been doing. You're going to find your du and solve for dx or whatever is in the problem with dx. You're going to substitute in and simplify. And then what you're going to do is use substitution to change the limits. So again, you're going to plug in your original bounds and you're going to substitute that into u to find your new limits. Now you have to be careful to keep the same order. So if you plug in the bottom bound, whatever number you get out, that's still your bottom bound. And if you plug in the top bound, whatever number you get out is still your top bound. Sometimes when you're working these types of problems, you have like, and it's not just these types of problems, really any type of problem, sometimes you're left with an additional x in your problem or x squared or something like that. Well, then you just solve for x using your u, and then you simplify that and plug that into your integral. And then lastly, you integrate and simplify. Alright, so in this next example, they just want us to set up the integral. They're not asking us to solve it or anything like that. We just need to set it up. So the first thing I need to do is find my u. And again, I'm looking for that inside function, which appears to be x to the 5th plus 3t. So t to the 5th plus 3t. And so my du is going to be 5t to the 4th plus 3 dt, which is this whole second piece of my integral. And so when I substitute my u in, I'm going to have the integral of square root of u, or u to the 1/2 du. Now my new bounds, basically what I'm going to do is I'm going to plug in this 0, this bottom bound, and I'm plugging in the 1 into my u. So plugging in the 1 into u, I get 1 to the 5th plus 3 times 1, which is 4. And then plugging in the 0 into u, I get 0 to the 5th plus 3 times 0, which is 0. So my new integral would be the integral from 0 to 4, u to the 1/2 du. Now, I'm not going to solve this all the way out, but what we need to understand is I would just integrate this in terms of u, and then plug in those bounds. I would never go back and put it back in terms of t or x or whatever. I'll just leave it in terms of u since I changed my bounds to be in terms of u. All right, so again, this is another just setup problem. And so I'm trying to figure out, again, what my inside function is. It doesn't appear to be an inside function in this actual case. So what I'm going to look for is something that I can let be u, where du would also show up in the problem. And since I know that the derivative of tan is secant squared, I'm going to let u be tan, or tan x. And so du is secant squared x, which is the whole second part of my problem. And so I'm left with the integral of u du. Now, getting my new bounds, I have u pi over 3, which would be tan of pi over 3, which we know from our unit circle is root 3. And then for the bottom bound, I'd have u of 0, which is tan of 0, which is 0. So my new integral would be the integral from 0 to root 3 u du. All right, so here's a harder example where we have extra variable in our problem. So we have the integral of x, 3 minus x to the 4th dx. And so again, my inside function here is 3 minus x. And so I'm going to let u equal 3 minus x. And I'm going to find du to be negative dx, or I can bring the negative to the other side to say negative du equals dx. So here I see I have the u, I have the dx part, but what the problem is that I have this extra x here. And so to get rid of that x, I'm going to take my u, or my original u substitution, which is 3 minus x, and I'm going to solve for x. And so when I do that, I get x equals 3 minus u. And so when I substitute back in this integral, I'm going to substitute the integral of x, which is 3 minus u, and then 3 minus x was u to the 4th, du, all with a negative on the outside because of the negative du. So I have negative integral 3 minus u, u to the 4th du. Now I'm going to distribute in this u to the 4th to simplify my integral. So I have negative 3u to the 4th minus u to the 5th du. And then I'm going to use my power rule to integrate this. So I'm going to have negative 3u to the 5th over 5 minus u to the 6th over 6 plus c. And then I'm going to plug my x back in, or my x in for what my u was. So I'm going to have negative 3 times 3 minus x to the 5th over 5 plus 3 minus x to the 6th over 6 plus c, noticing that I did distribute this negative to both terms. All right, so another example like that, we have x squared 2x plus 5 to the 4th dx. Again, I'm going to let my u be this inside of 2x plus 5. And so my du is going to be 2 dx, but I'm going to divide that 2 out. So I have du over 2 equals dx. And then I noticed that I covered this 2x plus 5 to the 4th part. I covered this dx part, but I never took care of the first part, the x squared part. And so what I'm going to do is I'm going to take my u sub, so this 2x plus 5, and I'm going to solve for x. So doing so, I get x equals u minus 5 over 2. And I'm going to substitute all that back into my integral. So I have the integral of u minus 5 over 2 squared times u to the 4th du. Now simplifying that, or squaring this piece, I'm going to end up with u squared minus 10u plus 25 over 4, but I pulled the 4 out, and that's how I got the 1/8 u to the 4th du. And then I'm going to distribute in that u to the 4th. So I have 1/8 integral u to the 6th minus 10u to the 5th plus 25u to the 4th du. Then using my power rule and keeping the 1/8 on the outside, I have 1/8 u to the 7 over 7 minus 10 u to the 6 over 6 plus 25 u to the 5 over 5 plus c. And then simplifying, changing my u's back to x's, and distributing that 1/8, I'm left with 2x plus 5 to the 7th over 56 minus 5 times 2x plus 5 to the 6th over 24 plus 5 times 2x plus 5 to the 5th over 8 plus c.